Hi statisticians, and welcome to our section 7.3 lesson video. So this is what the lessons are going to look like from now on. You'll see this page that's exactly the same notes that we fill out in class, and then I'll write on them just kind of like it's a whiteboard, and you'll hear me talking and we'll go through the notes just like we normally would. So last time we talked, we got through section 7.2, so we're starting here on section 7.3, and we have a warm-up. So just to refresh your memory about section 7.2, remember we went over our favorite normal curve, which is called the standard normal. Standard normal. And any normal curve looks a little bit like a bell curve like that. And the reason that we like the standard normal the best is because the mean is 0, and then the step size, the standard deviation, is 1. So this sort of steps out to 1 and then over to 2 and 3 and so on. This is sort of modeled just like a regular number line. So this one's our favorite. It looks like this. Now, the other thing that, first of all, okay, we like the standard normal because the horizontal axis looks like a number line, and these values are called z values, all of these. The other reason that we like it is that if you flip to the back of this packet, we have this big table that gives all the areas to the left of those z values on this curve. So it gives these left areas. Now, before we start, I want you to make one little change on this table. Notice that there's this top row here that says z and then 0.00, 0.01, 0.02, and so on. Before we get started, I just want to copy that exact top row onto the next page because we're going to be using this a whole bunch. So here's our z and then 0.00, 0.01, so that we just have a complete table. So do that before we start. .08 and 0.09. Okay, so we kind of went over last time how to read this table, but let me give you a quick refresher. These values on the left and across the top are the z-scores. So these are our z's. To show you a little bit better, these are our z's over here. And then in the middle of the table, this gives you the areas under the curve. So this says areas, I don't know if you can see it, but that's this area. Notice that all the areas are brought out all the way to 4 decimal places, and the z-scores are always, we express them rounded to the nearest hundredth. So for example, this value here, so this would be z equals 0.7, and then if you want your hundredth spot to be, say, 4, you would walk over to this column, 0.74. So these are your hundredths values over here. So 0.74 would be 0.74, and this is the area to the left of that z-score, 0.74, and then that's the area to the left. Okay, so inside the table, these are the areas. Outside the table, these are your z-scores. So we're going to be using this table a whole bunch. Let me just clean up what I just did, and then we'll go back to that warm-up. So on page 1, the warm-up says, let x have a normal distribution with mu equals 10 and sigma equals 2. So that's saying this is a normal curve, looks like that. The middle of it, the mean, is 10, and the standard deviation, or the step size, is 2. So if this is 10 and I take 2 steps, this is 12, and then 2 more steps, now this is 14, and 2 more steps, now this is 16. So that sort of gives us our step size. I can also go down 2 steps in this direction, so that would put me here at 8, 2 more steps, 6, and so on. Now notice this is not our favorite standard normal. Our standard normal has 0 in the middle and it has a step size of 1. So this is a normal, but it's not our standard favorite normal. We don't have a table for this one, right? So let x have a normal distribution with mu equals 10 and sigma equals 2. Find the z-score for x equals 11 and then find the z-score for x equals 14. Okay, so fortunately for us, we have a formula for this. Z equals x minus mu over sigma. This is a formula from last time. So I'm just going to plug in these values. The first one says x equals 11. So everywhere that I see an x, I'm going to put 11. Everywhere I see this mu, I'm going to use 10. And everywhere I see sigma, I'm going to put 2. And when I simplify this, 11 minus 10 is 1 over 2. And because we usually express z's in decimal form, I'm just going to write 0.5. And actually, because in the table we usually express z's rounded to 2 decimal places, I'm actually going to write this 0.50, which is a little bit weird, but you'll see why I did that in a second. Now let's do it again for x equals 14. So z equals, now everywhere I see an x, I'm going to put a 14, minus everywhere I see a mu, I'm going to put a 10, and everywhere I see a sigma, I'm going to put a 2. So 14 minus 10 is 4. 4 divided by 2 is 2. And again, you'll see why I'm doing this in just a second. I'm going to write this z value as 2.00 because we usually express our z values to 2 decimal places. Okay, so now that I have both of these numbers, z equals 0.5 and z equals 2, use the table on the last page of this packet to find the area. I should really say under the standard curve, I'll say to the left. Just put it in parentheses here. I really should say to the left, corresponding to each of the z values that you found in problem number 1. Okay, so I'm going to find the area to the left of 0.5 and also the area to the left of 2. So flipping back to that table, starts on page 5, notice that on this page, our z values are all negative. So all these are negative, which kind of tells me probably not going to find my value on this page. I'm going to go to the next page, and my first z value is 0.50. Okay, so the way that this table works is that I get the first two numbers, so the ones place and the tenths place, from this left column. So in this left column, I'm going to look for 0.5, and so there it is. So that tells me I'm in this row, and now I just have to decide how far over in that row to go, and that's where the hundredths place comes in. So here are my hundredths values, 0, 1, 2, 3, 4, 5, and so on. Well, I'm going to 0.50, so I'm going to go here, and this is the area value that I want. So for a z-score of 0.5, the area under the curve is 0.6915. Now this is really important that you understand from an early point, like right now, the difference between the z-score, which is the horizontal value, and the area. So it's like on this curve saying this value is 0.5, that means that this area in here is 0.6915. So z-score and area, and they're different things. We're going to be working with them throughout the rest of this chapter, so it's important to know the difference. The z-score is just that value across the bottom, and the area is actually the area under the curve. Okay, so we found the first one. Now, the second value that we're talking about was z equals 2. So let's start this process over. Let me just erase this mess that I made here. And we're finding the z value, no, we're finding the area for z equals 2.00. So again, I'm just going to use these first two, the ones place and the tenths place, on the left side of my table, and I notice that they are right here. And then 0.00 tells me I'm still in this first column. There's my hundredths place, and 0.9772 is the area. 9772. Okay, so I have my two areas, and I'm going to take those back to warm-up problem number 1. So this says, oh, it actually just says, just find the areas. Okay, so I found them. For z equals 0.5, our area equals 0.6915. Oops, not like that. 0.6915, and for z equals 2, the area was 0.9772. Okay, so one of the things that we saw last time was that finding the area under the standard normal curve is very easy because we have a table, right? So this is our favorite one. The middle is 0, the step size is 1. Unfortunately, in the real world, when you're given a distribution, first of all, sometimes it's not normal at all. But even when it is normal, it's maybe not this very, very friendly normal. In fact, that's what we just saw in the warm-up, right? We have a normal distribution, so that's great, but it's not our favorite normal. It's got a different mean from 0, and it's got a different standard deviation from 1. So basically, the process through the rest of this chapter is going to be the exact same thing. To find any area and any probability for a random variable that follows any normal distribution, doesn't have to be a friendly one, I'm going to give you an x value. But remember, we don't really like x values because we don't have a table for x values. So you're going to take whatever I give you, whatever x value, convert it to a z value, because for a z value we have a table. It's the friendliest normal distribution that we have. Convert to z, just like we did in warm-up problem number 1 using this friendly formula. If you have not committed this one to memory, we don't really have to memorize any formulas in this class, but this would be a really good one to memorize. And then you'll use the table, the z table that we have in the back of this packet, to find corresponding areas and probabilities. And just let me write a really, really important fact. We talked about this briefly in section 7.2. Area and probability are the exact same thing. So if I ask you for the probability, like I'm about to, probability that x is between 11 and 14, what I'm really asking you for is the area. Probability, area, tomato, tomato. So carrying the warm-up problem a little bit forward, let x have a normal distribution with mu equals 10 and sigma equals 2. This is the exact same setup from the warm-up. So these are the same, this is the same distribution. Find the probability that x is between 11 and 14. X is between 11 and 14. That's how you read one of these sort of compound inequalities. X is between 11 and 14. Now, probability is the same as area. So what I'm really asking you to do is find the area between x equals 11 and x equals 14 on this distribution, on that normal curve, right? But we don't have a table for that normal curve. So instead, what I'm going to do is convert those x values, that 11 and that 14, I'm going to convert those to z-scores or z-values because I have a table for z's. So in fact, we've already done this. We already converted 11 and 14 to those two z-scores. So I've done this part, which tells me that the probability that x is between 11 and 14 is the exact same as the probability that z, now I've converted to z is between 0.5 and 2. And I converted this x to a z, so now I write my inequality with z's here. This tells me I can use that z table. I'm on the standard normal curve, our favorite one, because we have a table for it. Now, probability, area, tomato, tomato. So what I'm asking you now is to find the area between z equals 0.5 and z equals 2. Now we found those two areas. This was warm-up problem number 2. So to find the area between them, I'm going to take the larger area and subtract the smaller area. So in the case of warm-up problem number 2, the larger area, the one that went with z equals 2, was 0.9772, and that smaller area, smaller because it's a little bit more to the left on the curve, was 0.6915. So I took the larger area, this one is associated with z equals 2, minus the smaller area, this one was associated with z equals 0.5, and when I subtract those, I get 0.2857. Now at this point in the video, you should pause and try the I really understand this problem number 1. So try this one. At the very end of the video, we'll go over the answers from this, but try this one now. Okay, so we're on page 2. Now this problem is interesting. I can give you x's and you can convert to z's and do your math there, which is what will typically happen, but actually the problem can go in reverse also. So recall from the previous section that we sort of rearranged that formula that looks like this. We rearranged this one, just doing a little bit of algebra. So like, for example, we multiplied both sides by sigma. That gave us z times sigma equals x minus mu. And then we added mu to both sides, and that gave us x equals z sigma plus mu. It's the same formula as this one, but it's just sort of written in a different arrangement. This arrangement is solved for x. So if I give you a z score or a z value and I'm asking you to solve for x, this one is a little bit faster, but you really could use either formula. So if you memorize this one, which you likely will, you can absolutely use this one also. Okay, so let's see an example of sort of doing this backwards. Let me just put a little star here. I really like this example, like say for an exam problem, I really like this problem. So for whatever that's worth, I suggest you know how to do this one in about 2 weeks for your Chapter 7 test. Okay, a video game company sells an expensive video games package. Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee policy will refund the full purchase price if the computer fails during the guarantee period. The research department has done tests that show that the mean life for the computer is 30 months, so average life for this computer is 30 months, with a standard deviation of 4 months. So here's our curve, assuming the computer life is normally distributed. So we have a bell curve. That tells us that the step size on this curve is 4 months, so that would bring us here to 34, over here to 38, 4 more than that is 42, and so on. And then we could do the same thing over here, go down to like 26, 4 more to 22, and so on. Notice this is not our favorite normal distribution. I mean, of course we love it because it is a normal distribution. We like these, but it's not our favorite one. Our favorite one has a middle of 0 and a step size of 1. So, assuming the computer life is normally distributed, how long can the guarantee period be if management does not want to refund the purchase price on more than 7% of video game packages? In other words, what is this life expectancy for these video games? Now, most of them will last somewhere in this area, right? Like the average is that they'll last 30 months before they have some kind of a problem. But some of them will last shorter. Some of them will last less time. So we want to know how many months is this? What is this X value? So that 7% of the computers fall into this area. We want to find the Z value on the table such that the area is closest to 0.0700. Now, the 0700 decimal came because this is just the decimal representation of 7%. So I want to find the area in the table of 7%. Okay, so here's what we know so far. Mu equals 30, sigma equals 4, and we want to find area closest to 7%, or in other words, 0.0700. I'm using 4 decimals here because that's what happens in the table. Okay, so walking over here to the table, back of your packet, notice that these decimals are in increasing order. So here's 0.00, scroll down, 0.01, and then 0.02, and 0.03, and 0.04, and we're looking for closest to 0.07. So we're going to have to Goldilocks this a little bit. We're going to find a too small and a too big. 0.07. Here's 0.07. Da, 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 da. Here's 0.0708. That's a little bit too big. And just to quantify that, 0.0708 is 0.0008 too big. Because I wanted it to be 0.0700. So that's 0.0008 steps too big. And then on the other side, 0.0694, there's our too small, and that is 0.0006 too small. If I take 0.0700 and I subtract 0.0694, I get this. Now, of the two of those, 0.0694 is the closer value. This one is closer because it's a smaller number of steps too small. So that's the area. This is the area. Now I need to find the z-score that goes with this area. So the z's are listed along the outside of the table. And remember, I get the first 2 digits, the ones place and the tenths place, from that left column, so negative 1.4, but then negative 1.4 what? I need to get the hundredths place, and so I get that from this column. Negative 1.48. That is the z-score that goes along with this area of 0.0694. Okay, so here's what we know so far. The area closest to 0.0700 has a z-score of negative 1.48. But this problem is asking about x values. It's not asking about z-scores. So I just have to, lastly, convert z, this z that we found, to an x value, because that's what it's actually asking about in this problem. Well, fortunately for us, we have a formula for this. This one, x equals z times sigma plus mu. Okay, so I'll use that here. X equals, now everywhere that I see a z, I'm going to put this negative 1.48. Here's the z times sigma, which was 4, plus mu, which was 30. So putting this into my calculator, negative 1.48 times 4, get that number and then add 30, and I find that x equals 24.08, which seems pretty close right here. X equals 24.08 months. So here's what that means on this curve. It means that if the company guarantees their video game systems for 24.08 months, it means that 7% of them will fall into this area. So that's the 7% where the company would offer refunds. Like if you buy this video game system and it only lasts for 22 months, you can apply for a refund. Now, 93% right? Everything left over after the 7%. 93% of these video game systems will last more than 24.08 months. So they'll be over here, and these people won't ask for a refund because their video game thing lasts for longer than 24 months. So again, this problem can sort of go one of two ways. I can give you an X and you use a Z, or it goes the other way and you find the Z value and then you can transfer it back, translate it back to X like we just did. So again, I really like this problem. I would have this in your back pocket for the exam, the Chapter 7 test. I really like this process. Now at this point you should pause the video and try I really understand this problem number 2, and we'll go over the answer to that one at the end of the video. Okay, so the last thing that we'll do in this section is decide whether data is normally distributed. So the idea is this. Pretty much in all the previous examples in this chapter, in this entire chapter, we're given a statement like this, that the data is normally distributed. You're looking at a normal distribution. Assume that X has a normal distribution. Okay, we're just told. But you're also going to be given a distribution of data like this one. So you're just given some raw data and asked, hey, is this normally distributed? Would this be modeled by a bell curve? Now, personally, I can't just look at this smattering of data and tell you yes or no. And so, fortunately, we don't have to. We've got 4 tests for this. And we're going to go through these one by one with this data. So, what you should do now is pause the video and in your calculator, input all of these values into list 1. So just a reminder for how to do this, you're going to put stat and then edit and input all these values, and I think there's 50 of them, into list 1. And try to do it carefully because you don't want to forget any of these. There's a lot of them here. Okay, so once you have these data values all stored in list 1, we're going to go through this series of 4 tests to determine whether this data has a normal distribution. Really, it's 3 graphs and then this one little formula. So the first thing is we're going to make a histogram. So in your calculator, you're going to click stat plot. And remember, that's sort of above that y equals button right at the top. So if you do second and then y equals, that takes you to stat plot. Now click on plot number 1, make sure that one is turned on, and it's going to take you to a screen that looks like this. And the histogram, the first graph that we're doing, is the 3rd one on the list, so just highlight the histogram, click there. Now make sure that your data is coming from the appropriate list. If you just put this into list 1 like I did, then make sure your data is coming from there. And then at the end of those 5 buttons right across the top, click the one that says graph. So when you click graph, the other thing that you might need to do here is click zoom. That's the middle button along the top, and then just option number 9, which does zoom stat, so that'll just zoom appropriately for this data. Okay, so that should bring you to a screen that has a histogram, and I'm just gonna draw what I see here. Remember, we're looking to see if this is normally distributed, so it should have like a generally bell curve shape. So mine has something like, it would be nice if I could just show you like we would in class, but doing the best we can, so I'll draw it here. Looks kind of like this, and then some shorter ones over here. Maybe this one's a bit too tall. Anyway, so that's kind of what my curve looks like. Now, when I look at this this histogram, I can see that it has sort of like a generally bell shape to it. Notice it's not perfect. Like this maybe seems like it might be a problem. It's also not totally symmetric on either side. Like some of these bars don't completely line up with their mirror images. So we're looking for generally normal shaped, but maybe not exactly. So in fact, I mean, that's the reason that there's 4 of these tests. It's because maybe one of them you're kind of like, looks like it, but maybe I want to see more. I would look at this histogram and say, this looks generally normal, but let's keep doing other tests. So test number 1, I would say, is okay. We passed test number 1. Test number 2 is that we check for outliers using a box and whisker plot. So this is really important. We haven't actually defined what an outlier is in this class yet. So outliers are larger than your third quartile by an amount greater than 1.5 times the interquartile range, or below your first quartile by an amount greater than 1.5 times the interquartile range. So 1.5 times the interquartile range is like sort of a key value here. And also just one quick note, there should not be more than one outlier, but one outlier is okay. One outlier is okay. More than one is not okay, but one outlier is fine. Okay, so I'm going to go back to stat plot. So click stat plot across the top, get back to this screen on your calculator. We're going to keep using that same data. We're going to do all 4 tests on this same set of data. But now instead of making a histogram, I'm going to make a box and whisker plot. So just select that box and whisker plot and then click graph again. If you need to adjust your zoom, you can. So again, you can do graph, and then if you need to, you can click zoom and then 9. It'll kind of re-center your graph for your new box and whisker plot. Okay, so then once you've got your box and whisker plot, and I'll draw mine down here, kind of looks like a rectangle. This is pretty much right in the middle, and then I've got fairly long whisker and then a longer whisker. Okay, so now I'm going to click trace. Trace is the 4th button right across the top. So click trace, and when I click trace, it brings up a little cursor, which is sort of flashing right here in the middle of that box and whisker plot. And actually what that tells me is that my median value, it says it across the bottom of the screen, the median is 19.5. So I'm just going to scroll around here. When I scroll to the left, it tells me that Q1, my first quartile, is 18. It tells me that my minimum value is 13. And it tells me that my third quartile, which is here, is 21. And my maximum value is 25. Okay, so remember the key on this second test is 1.5 times the interquartile range. 1.5 times the interquartile range. And if you don't remember, the interquartile range is just Q3 minus Q1. That's the interquartile range. Really important to remember that. This is not on your formula sheet, so you need to commit this one to memory. Q3 minus Q1. Also, on this picture, this is the interquartile range. It's just the length of that box in the box and whisker plot. Okay, so for us, the interquartile range is 21 minus 18. So 3. So then 1.5 times the interquartile range is 1.5 times 3, which is 4.5. Okay, so that's important because that gives us sort of like a limit for outliers. It tells me that 4.5 here is okay. Anything in here is okay. Now, 21 plus 4.5 is 25.5, so that's why I made it go just a smidge past this 25. Everything on this side of the box and whisker plot is fine because it's all within 4.5 of this Q3. Now over here, 4.5 brings us to this value, 13.5, which tells me 13 is outside that range, which makes 13 an outlier. So there's an outlier. Now remember, on test number 2, we said one outlier is okay. So it's okay that there is the 13, but now the next thing that we need to check for is in our data set, is there more than one 13 or is it just this one outlier? Because if we have another 13 in here, then there's a second outlier and that would indicate that we failed this test. So this data would not be normally distributed. But as I'm looking through this data, I think there's only the 113. So we've got one outlier, but that's okay. It's okay to have one. 25, this maximum value, remember that was still in the range of okay. 13 is an outlier, but as long as we only have one, we pass test number 2. So far, test number 1, the histogram, indicates that that big list of data is normally distributed, that this would look like a bell curve. Test number 2, the thing about outliers, well, we have one outlier, but that's okay. So test number 2 is passed. Test number 3 says to check for skewness. Remember, skewness is where a distribution might be kind of like pulled over to one side or another. So it kind of looks like that. Now, to check for skew, we use this formula for something called the Pearson's index, which is 3 times the sample mean minus the median over the sample standard deviation. Now, ideally, the Pearson's index equals 0. If it equals 0, that means no skew. But we say as long as it's between 1 and -1, that's okay. Anything bigger than 1 is not okay. Anything less than -1 is not okay. Ideally, it's 0, but really 1 and -1 is the cutoff. And if you get anything bigger than 1 or less than -1, we would say that the data is not normal, not normally distributed. So let's find the Pearson's index for our data. Now, oh goodness. So, not sure why. Don't know why. Okay. Sorry for that interruption. In this formula, we need to use the sample mean, we need to use the sample standard deviation, and we don't have those given to us. But fortunately for us, we already put in all this data into the list. So to get those statistics, what we're going to do in our calculator is click Stat, and then click Calc. Stat and then Calc. And because we just have one single variable, you're going to click one variable statistics. And then just click Enter a bunch of times. Oops. Make sure you're coming from the right list. Click Enter a bunch of times. And when I look at this list, okay, it tells me X bar, the sample mean, is 19.46. It tells me the standard deviation, that's the one with the S. Make sure you're not using sigma, we want to use the one with the S, is 2.704, I'll round it here, 70457. What else do we need? The median. It tells me when I scroll down on the list, the median is 19.5. And I'm going to use those values in that Pearson's index formula. So that's going to say 3 X bar minus the median all over S. So we're going to use these values to find the Pearson's index, which is going to indicate if there's any skew. Okay, so I've got the formula written down. So now I'm just going to plug in these values. Okay, so 3. Now everywhere I see this X bar, remember that's the sample mean, so 19.46 minus the median. Remember another name for the median is just the second quartile. So 19.5 here, and then divided by the standard deviation. And actually in your calculator it has a little X subscript there, but standard deviation, 2.70457. And when I put this into my calculator, careful with parentheses, make sure you get this numerator all together, you should get negative 0.0444. Now, remember, ideally the Pearson's index is 0. So 0 would mean there's absolutely no skew at all. But we kind of say, like on the number line, here's 0, here's where we want it to be. But as long as it's somewhere in this range, somewhere between -1 and +1, we'll tolerate anything in this for the Pearson's index. Now, out here, anything greater than 1 and anything less than -1, that means that our data set does not have a normal distribution. But as long as we're somewhere in this little neighborhood of 0, somewhere between -1 and +1, this is okay. And this certainly is. So that tells us that we have passed test number 3. And that leaves only one more test. So we've got test number 4, which is this thing called the normal probability plot. So this is a graph that we have not made using our calculator before. So you're going to go back to stat plot. So do stat plot and click on plot number 1. And remember, we just used this in the second test to do a box and whisker plot. But now we're going to scroll all the way over to the end here and select this very last graph. Mine actually looks a little bit different. It's not colored in like this, but the last one, make sure that your data is coming from the right list, and then click graph. Now again, you might have to do zoom and then number 9 to scale this in the most appropriate way for your data. Zoom and then number 9. But when I do this, I'm just going to draw it right here. Nope. Okay, I've got a horizontal axis, got some kind of dots here, and then my data, my normal probability plot kind of looks like this, but some of these have little like multiple points by them, and these sort of look sort of clustered right in the middle. And what's really important here, the thing that we're checking for, is that all of these points generally lie along a line. Now I know there's multiple points, like I said, there's these little clusters, so it's not perfectly linear, but if they lie close to a straight line, then the data is approximately normal. And when I look at this test, or when I look at my normal probability plot, they certainly do. So I would say that this data passes test number 4. And so we, again, made a histogram that looked generally normal. We checked for outliers. We found 1, but 1 is okay. We checked for skew using the Pearson's index. We want it to be 0, but we got negative 0.04, really, really close to 0. And then number 4, we made this normal probability plot, which we really haven't gone over, but all you're looking at is just that it's close to a line. And it is. So we passed all 4 tests, and now we can finally answer this question. Decide whether the data is normally distributed, and it is. We went over all 4 of those tests, and so we can say confidently that this data is normally distributed. Okay, so at this point, you can try this, I really understand this problem number 3. Now this is a way smaller data set, but you can pause the video now, put this into list 1, clear list 1, and put this in and do the exact same 4 tests and decide whether the data is normally distributed. You will be asked to, well, you might be asked to do this on the next exam, so make sure that you go through all 4 of those tests, even though it's rather tedious. Okay, so hopefully you've had a chance to try all of these problems. So let's go through these. The first one says, let x be a normally distributed random variable with mean equals 5 and standard deviation 0.5. And our job is to find the probability that x is between 4 and 6. Now, just like normal problems here, I give you x. You don't want to deal with x, so we're going to convert this over to a problem involving z. We're going to say this is the same as the probability that z is between something and something. Okay, so we've got all the values that we need to convert these x's to z scores. So I'm going to start with 4. I'll say I'm using this formula, mu over sigma. Again, this is a really good one to memorize. We're just going to be using it all the time. Okay, so 4 minus, now where I see a mu, I'm putting a 5. Over sigma is 0.5, and 4 minus 5 is negative 1. Negative 1 divided by 0.5 is negative 2. So that 4 becomes a negative 2 z value. And now I'm going to do the same thing for 6. So I'll do 6 minus 5 over 0.5, and when you do that, you're going to get a positive 2. Here, so I'm looking now for the probability that z lies between negative 2 and positive 2. And remember, probability is the same as area under the normal curve. So really I'm just looking for the areas associated with these two values, and then I'm going to subtract larger area minus smaller area. Okay, so I'm going to go to my table, and I'm going to start with finding the area for z equals positive 2. I've really made a lot of a mess on here. So here's the value positive 2, and we want positive 2 exactly, so 2.0. And remember, the 0.00 is this very first column. So here's 2.00, and the area associated with that is 0.9772. So we can write that number down here, 0.9772. Notice we're kind of going in opposite order because I'm actually using the larger z value to get this area right now. I'm going to do the bigger area minus the smaller area. So now I'm going to go back and get the area for z equals negative 2. Oops. And so negative 2, which is of course the same as negative 2.00. So negative 2.00. So here, 0.0228 and 0.228. And when I subtract those, I get a difference of 0.9544. And that is the probability that z is between negative 2 and positive 2, which is the same as the probability that x is between 4 and 6. Now the second problem says find z such that 2.8% of the standard normal curve lies to the left of z. Okay, so here's what this problem is asking. I'm going to draw my normal curve, something like this, and underneath this curve right now, like all of this area is 100% of the area. But this problem isn't asking about 100% of the area, it's asking about 2.8% of the area. So I just kind of want like a little sliver of this curve. I want this to be 2.8% of the curve. And specifically what we're asking for is this z value with a left area of 2.8%. Well, a couple of challenges here. First of all, the 2.8% is not in decimal form. So let's start by writing that as 0.028. And then let's actually tack on a fourth 0 because all those areas in the table are expressed using 4 decimal points. So 0.0280. Now, the other challenge is going to be finding that decimal value, this one, in this jungle of numbers. So they are in order. Let me try to clean up some of the mess I've made. They are in order. So I'm going to try to find something closest to 0.0280. Here's 0.026. All right, so I've got 0.0274. That one's just a little bit too small. And 0.0281. And that one's just a hair too big. But of those two numbers, the too small and too big, the 0.0281 is definitely closer. So I'm going to go with the z value that gives me an area of 0.0281. And that value is negative 1.9, and I just need the hundredth spot, and it's 1. Negative 1.91. So z equals negative 1.91. Okay, now the third one says consider the following data set and decide whether the data is normally distributed. So the first thing that you need to do is enter this data. I think there's 15 numbers maybe. Enter those values into your list. Okay, so I put this in list 1. And so now decide whether the data is normally distributed. There's 4 tests for this, and so I'm going to go through each one, and we actually need to kind of explain each test. I'm going to model this like what I'm hoping I can ask you to do on the exam, or what you could potentially be asked to do on the exam. Let's say it that way. Okay, so the first thing that we're going to do is make a histogram. So I'm going to go to stat plot, and I'm going to change my little graph selection. Remember, when I do stat plot, it takes me to a screen that looks like this, and so I'm going to select the histogram. Ultimately, I'm going to end up making 3 different graphs, but I'll start with the histogram. Make sure that my data is coming from the correct list, and then I'm going to click graph. And now zoom. Mine is not zoomed correctly because it's zoomed for that previous set of data. So zoom and then 9. Now my histogram looks like this. Let's see. I've got a bar, and then I've got a taller bar. And then they kind of taper off like this. And there's a little bit of a tail. This one might have a little bit of skew. Now, when I'm looking at this, it's not a perfect bell curve. That's one of the limitations of doing a histogram, but it does kind of have this like general bell curve shape. So things that you're looking at that would not be a bell curve might look like this, and then other bars. Like that would definitely not be normally distributed. This has like a generally normal shape. It looks like it might be skewed a little bit, but I would say so far the histogram test is okay. Now, test number 2 is to check for outliers. So I'm going to make a box and whisker plot. So I'll go back to stat plot, and I will select the box and whisker plot on here. And then graph again, and I'm going to zoom this one more time just to get the right window. So my box and whisker plot looks like, let's see, like this. The median is just a little bit to the left. It looks like you have a shorter whisker on the left side and a slightly longer, maybe, whisker on the right side. And now I'm going to click trace. This is kind of one of the really important steps in problems like this. I'm going to click trace because I need to get some of these values. So I'll just go from the left. I'm basically getting, remember we call it the 5-number summary. So I'm getting the 5-number summary here. The minimum value is 65. The first quartile is 73. The median, or the second quartile, is 78. The third quartile is 85, and the maximum value is 94. Now, one of the really important numbers that we're going to use when we're checking for outliers is the interquartile range, which is just the length of this box. It's also the third quartile minus the first quartile. So 85 minus 73 is 12. And now I'm going to do 1.5 times the interquartile range, so 1.5 times 12, which is 18. And basically, that gives me limits on how far we can go in either direction, how far left or right outside of the box. Now, from 85 to 94 is only 9 steps, so definitely it's well within this 18 step radius, this 18 like allowable distance. And from 73 to 65, again, well within this 18 allowed distance for outliers. So we're okay, there are no outliers in this data set. No outliers. So we definitely passed the outliers test. Now again, remember, you can have one outlier, but more than one is kind of like, that makes you fail the normal test. Also, let me just point out, this answer was wrong. We got 0.9544. This is correct. This is not correct. Okay, so now the third test is the Pearson's index, which checks for skew. It looks like we might have a little bit, but remember, as long as it's less than 1 or greater than -1, it's okay. So Pearson's index, and the formula for that is 3 times the sample mean minus the median over the sample standard deviation. And I'm going to click Stat and then Calc and one variable statistics, and that's going to give me all these values that I need. So the sample mean for this data set is 78.2. The median, getting this from my list, is 78. And the sample standard deviation is 7.72935. And when I throw all of this into my calculator, let me do it. So 7.2935. Okay, so I'm finding a Pearson's index of 0.0776, about. I don't know. I'll tell you how much to round this exactly on the exam, but I'm going to stop at 4 decimal places, not sure why. Now, this is a perfectly acceptable number for the Pearson's index. What's really important is that this number is less than or equal to 1. Let me check exactly my phrasing on this one. Yeah, anything less than or equal to 1, and also it's definitely greater than or equal to -1. So that's what we're looking for. This is okay. We passed the skew test. So the last graph that we're going to make is called a normal probability plot. So I'm going to do stat plot again, and then I'm going to scroll in this screen over to this very last graph, which may or may not look like that on yours, and graph that one. And I'll zoom this one more time. Zoom stat. So zoom and then 9. And when I look at that, let's see. I've got something that kind of looks, I'm just really sketching this very loosely here. Something looks like that. And what's really important is that it generally looks like a line. Now again, you can click trace on this graph. You can do trace on your calculator and it will tell you exactly what these values are. It'll tell you the x and the y coordinates. So if you're curious like what exactly these values are, you can definitely click trace and you'll just jump through all the different values. but all we're really looking for is that it's generally in a straight line. And that certainly is, so all 4 of the tests seem okay, and I would say yes, this data is normally distributed. Okay, so you're now ready to do section 7.3 homework. Keep this table with you. We're going to need this for the entire rest of the chapter 7 notes. You also have this in your formula packet, like the one that you'll use for the test, but definitely keep this with you. We're going to use it a ton. Actually, not just for chapter 7, we're going to use it for chapter 8 and chapter 9 and potentially chapter 11 if we get there. So certainly keep this with you. I had recommended, I think in class, that you dog ear this page just so that you can get to it easily. But you're ready to do the section 7.3 homework, and I will see you for the 7.4 video.